Hello everyone and welcome to this video on logarithms. So for starters, what is a logarithm? As we know, a logarithm is the inverse of an exponential function. And the simplest way for me to remember it is whenever I get asked what a logarithm is, I automatically think that a logarithm is an exponent. And the easiest way to remember is to repeat it with me. A logarithm is an exponent. So let's take a look at some examples as to how a logarithm could be an exponent. Feel free to pause the video at any given moment. Well, first we start off by writing out our equation. I thought of an example such as log base 2 of 8 equals question mark. Notice how I said log base 2. This automatically shows that the first thing we write out is the base, 2 in this case. This will really help you when you try to transform the logarithmic function into an exponential function. And then of course I said of 8, meaning that the answer at the end should be 8. Remember how we said that a logarithmic function is the inverse of an exponential function, and that a logarithm is indeed an exponent? Well, this is what you should think of when reversing a logarithm into an exponential function. Since we know that a logarithm equals an exponent, then we could automatically write out our exponent, in this case would be over the base of 2, because we know that log base 2, 8 equals that exponent. A log is an exponent. Therefore, what we should write out at the end is 2 to the power of question mark equals 8. And then of course, when we try to find out the answer, we can inverse it back into log and have log base 2 of 8 equals our answer, which will be 3. Now let's take a look at the relationship of the graphing form of both the exponential and the logarithm function. To keep in mind, the logarithm function parent equation is log base 10, and then of course in the middle is x plus 0 because there is no horizontal shift, and then plus 0 because there is no k or vertical shift. And of course the vertical asymptote would be x0 and the locator point would be 1, 0. X equals 1, y equals 0. For starters, what you need to know is that to switch a logarithm function into an exponential function, you must do exactly as what it is. Like, we know that it's an inverse. We know that a logarithm is an inverse of an exponential function. Therefore, since we inverse the equation, we will also inverse the coordinates. Now let's say, for instance, we have the coordinates of 1, x equals 1, and y equals 0 for the logarithm function. Well, to find that for the exponential function, we switch the coordinates, and therefore we'll have x equals 0 and y equals 1, which is exactly what we see when we graph both equations. We'll have x equals 1 for the logarithm and x equals 0 for the exponential. And the same thing, let's take coordinates, for example, such as x equals 10 and y equals 1 for the logarithm. Well, now we know that x must equal 1 and y must equal 10 for the exponential function. And it works out perfectly because they are inverses, which is a way to verify. Another way to verify is looking at the asymptotes. The vertical asymptote for the logarithm function would be x equals 0. Well then, for them to be inverses, the horizontal asymptote for the exponential function, because it has no vertical asymptote because it's an exponential, would be y equals 0, which is the case here. It's correct. Well, let's take a look at something else. Let's take a look at the domain and range, because, well, we know that they're inverses, therefore the domain and range must be inverses of each other. Well, let's look at the domain of the logarithm function. We know that the domain here would be all numbers greater than 0, because as we remember, our vertical asymptote is x equals 0, therefore it will be all numbers greater than 0. And our range will be all real numbers because it's our range, and it just goes on. Well, now let's take a look at our inverse, the exponential function. We know that we inverse the coordinates, we inverse the equation, and we will do the same for the domain and range. Therefore, in this case, our domain of the exponential function will be all real numbers, and our range will be all numbers greater than y, because we will switch up the domain and range. So now our domain went from any number greater than x, because that's our vertical asymptote, to our range, any number greater than y. are horizontal asymptotes. Just like exponential functions, logarithmic functions have their own laws, or properties. The first property of a logarithmic function is log base a of m times n would equal log base a of m plus log base a of n. The second property is log base a of m divided by n would equal log base a m minus log base a of n. And the third property would be log base a of x to the power of n would equal n log a of x. Right off the bat, you should be noticing that there are similarities between the laws of exponents and the laws of logarithms. And just like the laws of exponents, the laws of logarithms must be verified in order to be true. In this case, let's take a random law of logarithms. Let's say the first one, which states that log of base a, m times n, would equal log base a m plus log base a n. And first, we have to choose a base. So in this case, I just chose b because it's easier for my brain to remember. And we start off by verifying. So let's say b to the power of l equals m, and rewritten as log would be log base b m equals l. And then b to the power of p equals n, and rewritten the same way, log base b n equals p. And now let's use the laws of exponents to combine both, and say base to the power of r, a new variable, equals n plus m, excuse me for writing n times m, it's m plus m, equals in log form, log base b n times m equals r. And now let's write that down again in a more simplified term. Now that we have all our variables, it would be b to the power of r equals b to the power of l times b to the power of p. And then b to the power of r equals b to the power of l plus p, based on what we know on the laws of exponents. And then since the bases are the same, we will say r equals l plus p. And then of course, we're going to write it all down into the longer version. It would be log base b n plus m equals log base b n plus log base b m. Feel free to pause the video to take a look at the verification process of the laws of logarithms. The nice part about the laws of logarithms is that the second property is exactly the same as the first one. The only difference is that when you divide, you subtract rather than add. And here's a picture of the same exact process with the slight differences adjusted. For the third property, I personally find that it's the easiest one to verify, and here's why. And also, I apologize in advance for the rotation of the camera. It's just how it went when I was filming it. And so for the third property, we know that log base a x to the power of n equals n log a x. For this exact property, I took 2 as my n just to make things easier, and you'll see why in a second. And then we say that log base a x to the power of 2, which can be rewritten as log base a x times x, because remember that we have 2 x's. And now it equals log base a x plus log base a x, because we know that when you multiply according to the laws and properties of logarithm, you have to add. So then that could be rewritten as 2 log a x, because we know that we have 2 different ones, because when we multiplied x times x, we also added. And when you have x plus x, you can simply rewrite it as 2 log base a of x. And for this property, you can really choose any number you want depending on your preference to verify. Like, for instance, let's say you chose 4. The only difference is that at the end you'll find 4 log base a of x rather than 2. And that's completely fine. You can verify it using any number you want. This is a concept map I made that will hopefully help you visualize the important parts of this lesson in a more clear way. Thank you for watching, and make sure to like and subscribe.